Welcome everyone, this is chapter 12 of the Crystal Clear Electronics video series. We present this chapter called Debugging, Troubleshooting in the program in 4 separate videos. Today's lead presenter for the third time is Szabolcs Pájer. My name is Gergely Lagler. You may have met me in our previous videos. If this is not the case, I recommend you also watch the videos of all the former chapters because these materials build upon each other and might offer even the most experienced viewers something new. I graduated in 2005 as a high school student at Elte János Bolyai Practicing High School in Szombathely, where I received a deep science education, and thanks to this, I decided to become an electrical engineer. So here I am, trying to teach you about crystal clear electronics.
Hello and welcome to you all. I'm Szabolcs Pájer. Gergő has already introduced me briefly. I've been teaching at the school he mentioned for quite some time now, and obviously that's how we met. I had the pleasure of being his teacher.
The 12th chapter of the curriculum was written by Dávid Kiss and proofread by several ex-Stalin members, including Gábor Proksa. Like all our writers and speakers, they are excellent experts, bringing us real-life examples. I tried the examples for this chapter beforehand. Since we want to show examples of debugging, the initial codes, just like it is often the case in engineering, work, but not well. They don't work as expected. We spend much time racking our brains and looking at them with piercing eyes while we fix the lines, causing unexpected functionality. Let's see what options we have for troubleshooting and correcting the errors.
Processors can perform various operations on binary numbers, such as addition, comparison, and other logical operations. In order to do useful tasks for us, we need to tell the processor which operations to execute on which numbers. These commands are called instructions, and the set of all the instructions is called an instruction set. You can assign a binary number to each instruction. By doing this, we have solved the problem, because if we want to give a command to the processor, then we need to send a binary number, which will tell the processor what to do. The processors of microcontrollers work on the same principle. They read numbers out of the program memory one after another, and execute instructions based on them. But how does an instruction get into the program memory? The easiest thing would be to write the binary numbers belonging to the instructions, so to speak, manually in the memory. We could do this if we only have a few instructions. However, it would take a long time to type them in case of longer and complicated programs, not to mention the amount of possible mistakes. That's why the assembly programming language was invented. In assembly, the instructions are not referred to by binary numbers, but by a short text, for example for addition, with the instruction called ADD. After writing a program this way in assembly, another program translates this text into binary numbers, that is, instructions. The only problem with this method is that different processors may and do have different instruction sets, so we would have to write different assembly code on each processor. This problem can be overcome by using high-level programming languages, such as the C language. C code lines are compiled into assembly language by a computer program, and then the compiled assembly code will be assembled into machine binary code. The first figure shows the C source code, which is what we can read easily. Of course, our program may not consist of only a single file. The operation of a program can be described with several files with C and H extensions. The content of such a C file can be seen in the picture, and you will most often encounter these files during the chapter. The first step in the compilation is done by the preprocessor and the compiler. The compiler converts the source of high-level C language into lower-level, so-called assembly language code. We can see this code in the middle step. This file still contains readable information for human mortals. The assembly code implements the functionality required by the C source with the processor's limited instruction set. From here on, we are only one step away from the machine code. As it was mentioned before, the assembly file can be matched one-to-one to machine instructions, only the words have to be replaced with the correct sequences of numbers. Let's look at the figure. The last step is completely hidden from us. The computer solved this problem as well. We already had several source files in our previous simple programs, and they are compiled to as many of these small sequences as many files we have. However, we can only upload one to the processor at a time, so as a last step, the so-called linker links these files to one whole.
Szabolcs, you just showed us both C assembly and the machine code. I'm afraid our viewers will be scared of the assembly and the machine code. I would like to point out that in the curriculum, we will mostly program in C, which will be easy to understand. Assembly and machine code will only be used by the compiler and the microcontroller.
That's right, Gergő. That's exactly how it is in the curriculum.
So we shouldn't be scared, right? Thank you.
Of course, this process is far from trivial, because the same C code can be implemented in several ways in assembly. The compiler optimizes the code, executes some things in a different order. If we do not use, for example, a variable, then the compiler will not create it unnecessarily. Fortunately, we can turn off optimization, and then what happens is exactly what we described. During the chapter, we will switch it off to avoid any misunderstanding. There are still programs that are written in assembly language today. One of the reasons for this is to control execution time and program size. When using assembly, you know exactly how much space is occupied by each instruction and how many clock cycles it takes to execute them. Unfortunately, it's not always possible to predict in advance what kind of instructions the compiler will use to implement our program written in the language C. The other reason is that we want full control over the processor. The code written in assembly is clearly translated into machine code. The processor executes exactly what we have written. The C compiler is also a program made by humans, so there may be errors in it. In some cases, it can misinterpret our program written in the language C. Now that we know how our code is compiled, we can look for errors in it. During development, the first requirement is to write syntactically correct code. We have discussed how to do this in earlier chapters. However, correct syntax alone does not mean that the code behaves the way we designed it. The processor executes commands millions of times every second, or more, so we have no chance to follow it with the naked eye. On the other hand, even if we could, we can't really see the flow of things because it is very difficult to look at the dance of electrons in the silicon chip. These problems are overcome by debugging, which is the process of troubleshooting. We have the ability to run our code step by step, track the status of the different registers and variables, and thus verify that the operation is correct.
We should debug the studio, Szabolcs.
That's right. A fly has been flying around here for a long time and we won't be able to continue working like this if it bothers us constantly.
Does this have anything to do with the name of this chapter?
Yes, it's not really about the flies. A very, very long time ago, sometime before semiconductors, electron tubes or relays were used to execute sequences of instructions on early computers. Yes, huge machines were needed. In such large rooms, the enormous amount of parts took up an enormous space, and these small animals, such as bugs, had the opportunity to either short-circuit, if undesirable, or break various contacts. It took a lot of time for programmers at the time to find the bug, and it happened several times that one of these unwanted visitors caused the problem.
Or the bug resistance fixed the error.
Programmers may not even have known that the bug created a new process.
Szabolcs, I think the time has come to take long strides on lead wings into the green-smelling, bumpy field of practice.
I get it, it'll be so. In the next video, we'll deal with this through an example. See you!
Bye!